everyone. We finished off the section on determinants. We will come back to the determinants later on in this course. We'll come back to the determinants later on in this course. We'll see that we need determinants to calculate eigenvalues and eigenvectors. And in fact, eigenvalues and eigenvectors are going to be useful to solve particular types of differential equations. So we have a little bit of an intermission here. We'll do some differential equations, we'll go back and do some more linear algebra, and then we'll do some more differential equations again. Right? So I just want to start today by explaining what a differential equation is. So a differential equation is simply an equation which relates an unknown function, call it f or y, whatever it is, it relates an unknown function to one or more of its derivatives. So a differential equation relates let's say an unknown function f to one or more of its derivatives. And one of the first things that we're going to need to do when we look at differential equations is decide what type of differential equation we're looking at. Right? Because different types of differential equations can be solved in different ways. And there are really a couple of important things that we look for when we look at differential equations when we are trying to classify them. Right? So the first distinction that we make is between ordinary and partial differential equations. And in fact, I'm mentioning this distinction, but we're not going to discuss partial differential equations in this course at all further. But let me explain what it is, and then we'll only deal with ordinary ones. So if f is f of x, right? So if f is really just a function of one variable, and the derivatives are df by dx, second derivative of f, right? And if the derivatives like this are ordinary derivatives, then we say this is an ordinary differential equation. And this course we're only going to actually solve ordinary differential equations, but I at least want to explain what partial differential equations are. For ordinary derivatives, then it is an ordinary dE, and that's sometimes abbreviated to ODE. Otherwise, you might have a function f. If f is f of xy, or f of x1, x2, xn, right? If you've got a function f which isn't just a function of one variable, it's a function of many variables, and the derivatives that appear in the differential equation are not just ordinary derivatives, but they're partial derivatives. So you have a partial derivative of f with respect to x, partial derivative of f with respect to y. Then it's not an ordinary differential equation, it's a partial differential equation. And partial differential equations turn out to be more useful, but also a lot more difficult to solve. Right? And the derivatives this gets abbreviated PDE, and let's just make that remark. In this course, we deal only with ODEs. In some sense, this is actually quite a big gap in your education, because you don't have another mathematics course. I don't know if you're going to see PDEs anywhere else. But definitely if you hang around and do a master's in engineering, I don't know, some of you will, you'll suddenly discover that you're up to your neck in PDEs and you've never had any training at all, and life becomes very difficult. Okay. So that's the one thing that we can distinguish. We can say we've got a differential equation. It's either an ordinary differential equation because your function is just a function of one variable, or it's a partial differential equation because it's a function of many variables. We're not going to worry about partial differential equations. We're only going to look at ordinary differential equations. The other distinction we can make is between linear differential equations, generally they're easy to solve, and nonlinear differential equations. Generally they're very hard to solve. So we'll spend a little bit of this course speaking about the nonlinear differential equations, particular types of nonlinear differential equations, the ones that we can solve. But most of what we're going to talk about are the linear differential equations. And what we'll see is that almost everything we know about linear systems of equations, or systems of linear equations, there's an analogous result for linear differential equations. So a lot of what we've already done in this course, we get to just, we'll basically be doing again. And we'll see how it applies, instead of to algebraic equations, how it applies to differential equations. Okay, so the other distinction, we also distinguish between linear and nonlinear differential equations. And the very short way of writing down what a linear differential equation is, and we'll do this in more detail later on in the course, but a linear differential equation, here's the short version. A linear DE let's just say, in fact, make it ty. So a linear differential equation can be written in this form. And this is maybe something which should make us think of the following. It should maybe make us think of the following. Right, we'll see that linear differential equations can be written as a linear transformation acting on a function gives us another function. And everything that we've done up until now in the course, we've been really thinking about things like a matrix, which is a linear transformation, acting on a vector gives us another vector. So linear differential equations are differential equations which sort of are going to have, in some sense, the same form as the problems we've already been thinking about. It means that we get to reuse a lot of the results. Okay. Let's just say where T is a suitable linear transformation. Okay, we'll do this in more detail later on. We're first going to just sort of do some other nonlinear differential equations, which, were actually, I think this is supposed to be a revision of some things which you may have seen very, very briefly at the start of this year. So we're going to start talking about, there's one other thing that's very important. Nearly forgot. In addition to classifying differential equations in terms of whether they are ordinary differential equations or partial differential equations, whether they are linear or nonlinear differential equations, we also are very interested in the order of a differential equation. And the order is basically just the biggest derivative that appears. So if you've got a differential equation which has got a third derivative in, and a second derivative and a first derivative, we'd call that a third order differential equation. So all differential equations are going to be at least first order. And generally, as the order gets higher, solving the differential equation becomes more difficult. So the order of a differential equation order of a differential equation. It's the biggest derivative that appears in the differential equation. Maybe it's just worth writing down a couple of differential equations and saying whether they're first order, second order, and so on. Right. So we could write down something like this. We could write down something like this. We could write down something like this. And we can think about what all of these various differential equations are. So if we look at that first differential equation, I can actually tell you what that first differential equation does. That first differential equation, we'll talk about it later on in the course. It's a second order differential equation because we've got second derivatives. It's an ordinary differential equation because those are ordinary derivatives. It turns out to be linear. We'll see why it's linear later on in the course. And that is an equation which describes the behavior of a damped harmonic oscillator. So if you've got, a pendulum swinging backwards and forwards, making small oscillations, you could use that to describe its behavior. Or if you've got a weight on a spring, sort of moving backwards and forwards, that describes its behavior. And we'll see that omega is in some sense the natural frequency of the system, so that's the frequency of the oscillations of your pendulum. And gamma over there we'll see is a damping strength. That's how much energy is being lost to friction or to vibration or heat or whatever it is. So this over here would be a second order linear ODE. And in fact, I can tell you what it is. This is a damped oscillator. This next equation, we're not going to discuss this in this course because it's a partial differential equation. Here, we've got a partial derivative here. But it's a second order partial differential equation, second order because there's a second derivative. This also turns out to be linear. We won't discuss why it's linear because it's a PDE. But I'm just putting this up. This over here is also a very well-known equation. This is the heat equation. And the heat equation basically tells you, in this case, in a one-dimensional object, how heat diffuses in that object. So that's a linear PDE, second order. Second order linear PDE. This is the heat equation. So if you've got, a metal bar, and you put one end of the bar in a bath of ice, and you put the other end of the bar in a fireplace, you want to know what is the heat profile on that bar after a certain amount of time. The heat equation tells you what the heat profile is. And then this over here is a first order differential equation, and it is very nonlinear. There's all sorts of nonsense going on over here. This y appears as a y squared instead of just as a y. It also appears inside sine and being multiplied by, this is just absolute nonsense, and I don't think this differential equation models anything useful at all. So let's write this down. This is first order nonlinear ODE, and it's not at all useful in any way, I don't think. I just made it up as I wrote it down. Okay. So what we're going to look at today, a particular type of differential equation, we're going to look at separable differential equations. And this, I think, might be something that you Might be something that you only saw in the mini semester. Is that right? Yeah. Okay. Oh no. Fine, okay, you'll stay there. Right, separable differential equation. So a separable differential equation is first order differential equation, a first order ordinary differential equation of the following form. A it's got this form. It's the first derivative over here, dy by dx is equal to, and then there's a function f which depends on x, and it's multiplied by a function g which depends on y. Okay. This is a separable differential equation. And it's separable because in some sense the dependence on x and y is separate, right? It's not like we've got x's and y's all muddled up. All the x's are over here, all the y's are over here, and they're just simply multiplied together. Does anyone remember how we solve a separable differential equation? Sure, yeah. So to solve a separable differential equation, we separate. So to solve this, you would do the following. You divide through on both sides by g. And you've got to be a little bit careful. You've divided through here. And when you do this division, you're making some sort of implicit claim, right? So let's just say NB. This assumes that g of y is not equal to 0, right? You can only divide through like this if that function g is not equal to 0. So what we should do at the end is, after we've done all of this, we should check whether g of y equal to 0 is a solution. So check if g of y equal to 0 is a solution. So this over here, we'll do all of this, but then we should always just go back and check whether we may accidentally have lost the solution when we divide it through over here. So to solve, you divide through. You integrate now on both sides. So you would integrate on this side with respect to x, and you would integrate on this side with respect to x. And we can invoke the chain rule here on the left-hand side. And this is very nice now, because on the left-hand side you've got an integral of something. Your integrand depends only on y, and you're integrating with respect to y. And on the right-hand side you're integrating something which depends only on x with respect to x. Yes?
If g of y equals 0 is a solution, then all your other solutions are still valid, and that's just an extra one?
Yes, this is just an extra one which you might not find by this method. Yeah. Okay. So we do some integration, and we get two new functions. We get whatever this is. We get some function, call it big G, when we do this integration. And over here we get some function big F when we do the integration. And we get a constant of integration. And this is now an implicit relationship between x and y. This is an implicit relationship if possible, and not always possible, if it's possible, and it won't always be possible, you try to get y by itself, right? And then finally, if we were given any information about y, so if they said that when x is equal to 0, y must be equal to 5, if they specified some initial condition like this, you would be able to solve for this constant of integration. In fact, actually, you can even solve for the constant of integration if you can't get an explicit relationship, but let's just add that in as well. And then whether or not So whether or not we have an explicit relationship, we should solve for C if we are given sufficient information. So in a moment I'm going to write up a separable differential equation, and I'll give you a couple of minutes to work through it. But are there any questions about this procedure here? First at the front.
Does this only work for first order equations?
Yeah, so if this was a second order differential, maybe there's some way to adapt it, but yeah, this is only going to work for first order.
Is there any particular reason why big G of y doesn't also have a constant integration?
Oh yeah, okay, so the point is, let's say we have a constant integration over here plus a, and a constant integration over here plus b. So a and b are just real numbers. So you bring a across to the side, and now you have b minus a. If b is a real number and a is a real number, b minus a is a real number. Call that real number c. Right, so you don't need the constant integration on both sides. Effectively, they just get absorbed and appear in one place. Right. Yeah. You would say, well, you set g of y equal to 0, then you calculate the derivative, dy by dx, and then you substitute that expression in. So g of y will be equal to 0, and you check if dy by dx is also equal to 0. Yeah.
How does the function g act on the side as an inverse?
You mean this? Okay, so if you get like a y squared here, right, then this would just be take the square root on the other side to get y by itself. Or if it was, you've got a cos of y, then you would take arc cos on the other side. Just try to get y by itself is what we're saying. All right, so here's an example. Solve Okay, so we've got y prime is equal to x squared of y, and we want to find all the solutions. In fact, we're actually only going to find one solution because we've got a particular piece of information here. We want to find the solution which satisfies when x is equal to 0, y should be equal to 1. All right, so go ahead and solve this. So this is how I solve it, right? So I started just by dividing through by the square root of y. And this is the sort of thing that I just set here on the side, right? So when we divide through by the square root of y, we're assuming that the square root of y is not equal to 0. So we know that we're not going to get the square root of y equal to 0. We're not going to get y is equal to 0 out of this procedure here. So we should check that separately. And I can immediately see that y is equal to 0 isn't going to work just because it doesn't satisfy that condition over there. It doesn't satisfy y at 0 is equal to 1, right? If we didn't have that condition, this would actually work, right? Because then dy by dx would be equal to 0. So the left-hand side, y prime would be 0. And the right-hand side would just be x multiplied by 0. So that is a possible solution to this differential equation, but it's being ruled out by the fact that it doesn't satisfy this condition.
I don't understand how you can see that indicated.
How do I see what exactly?
That y cannot be 0.
Well, I mean, so I've divided through by something, right? I divided through by the square root of y. So I'm not allowed to divide through by 0, which means that the square root of y is not equal to 0. Where is the square root of y not equal to 0? Well, it's when y is not equal to 0. So this is the one sort of thing that's been excluded, y being equal to 0. And then if y is equal to 0 anywhere, is it possible that y is equal to 1? No. So it can't satisfy the equation. Or it can't satisfy that condition that came along with the equation. Yeah. Okay, so yeah, what were we doing? Oh yeah, we divided through here by the square root of y. And having divided through by the square root of y, we then integrate on both sides with respect to x. We invoke the chain rule. So the left-hand side is just the integral of y to the power negative a half. Right-hand side is just the integral of x. You do this integration. This is a pretty easy example. You've had, what, a year and a half of maths. So we could, in principle, ask you to do more complicated things. Maybe you would have to do partial fractions or integration by parts or trig substitution or whatever it is. This could be more difficult, right? This could be more difficult. So we do this integration, and I have maybe done this in a different order to what you did. You could either calculate the constant c and then find an explicit relationship between x and y, or you can find the explicit relationship first and then calculate the constant c. It doesn't matter which one you do, you should get the same answer. Over here I've calculated that constant c first, and then you just rearrange and you get y by itself. All right. Are there any questions about this example? Okay, so let's take a look at another example. And we're going to look at a fairly long example, or maybe a little bit more interesting than this one. And it's going to be an example on orthogonal trajectories. So here's the question. We're going to look for a family of curves that is orthogonal to another family of curves to we want to find a family of curves that's orthogonal to these curves over here. So what are these curves over here? Hyperbole. Yeah, that's right. So these are hyperbole. Maybe we can ask a very tricky question. What's the difference between x squared minus y squared is equal to c and x squared minus y squared is equal to c squared? Does that change the family of curves in any way? How? Who thinks changing c to c squared changes the family of curves? Go on, put your hands up, nice and high. Okay, so there's like one person. Who thinks changing c to c squared doesn't change the family of curves? Oh dear, right? This really is very important. Okay, so so if you just write it like this, c might be positive or negative. If you write it like that, c squared is now must be positive. Okay, so if it's positive or negative, you can really think about this as being x squared minus y squared is equal to a squared, or x squared minus y squared is equal to minus a squared. And this, of course, means that you can change your signs. So if it's just x squared minus y squared is equal to c, you get hyperbola that lie horizontally and hyperbole that lie vertically. If it was x squared minus y squared is equal to c squared, then you only get, I think, the horizontal hyperbole. Yeah. Be careful. And next time, be more confident in yourself. Right? Okay, so find a family of curves that's orthogonal to the curves given by this over here. Let's actually just quickly draw a picture. We can maybe get a sense of this. I'm going to just push this over to the side and see if I can fit it in over here. So we're going to have that and that. I'm not going to draw all of them. And this. This. Okay, maybe I am going to draw all of them. This. This. Okay. So we're looking for a family of curves which is orthogonal to the curves given by x squared minus y squared is equal to c. So we're looking for a second family of curves where if we draw the second family of curves, as any member of the second family of curves passes one of these curves, they should pass at 90 degrees. Okay. Maybe just geometrically you could already make a good guess for what those functions could be. Does anyone want to make a guess? Family of exponential functions. No, exponentials won't work. We'll get to it. We'll see. Okay, so let's try and solve this. So maybe let's just make a note that I drew that family in blue. So what do I know about two curves if they cross perpendicularly? Do I know anything about them? Dot product is 0. Dot product of what? No. The gradients are negative reciprocals of each other. Yeah. Another way of saying that is that if you take the product of the gradients, you must get minus 1. Okay. So let's start by calculating the gradient for this function over here. Right. So we take the derivative on both sides. So we get 2x minus 2y dy by dx is equal to 0. We just differentiate implicitly. We rearrange this. Dy by dx. Okay, so we're going to divide through by the 2. We take that across, divided by the minus, so we get equals x over y. Okay. So that was the original family of curves. The original family of curves must have this over here as its gradient. The new family of curves dy by dx should be equal to, so what is the gradient of this new family of curves going to be? Negative y of x. All right, go ahead and solve this. Right, this is now a separable differential equation. Yeah, you have a question.
Geometrically, wouldn't it be the same family, just shifted with both?
Yes. We should find. Maybe I'll just draw in one of these. We'll find that we get something like this. Okay, maybe my drawing isn't super accurate, but we'll get more hyperbola. Just like that. Okay, but we'll come back to that later. For now, go ahead and solve this differential equation, and this is quite nice. We know what our differential equation, we know what the solutions should be, having made this guess. We expect that we get hyperbola as our answer. Cool. Yeah. All right, so we solve this. We have dy by dx is equal to negative y over x. I've divided through by y because I wanted to separate, which means that I've sort of said y is not equal to 0 when I've divided through by y. So we should actually go back and check that, see whether or not y is equal to 0 is a solution. It turns out that it will work. But let's just leave that alone for now and let's keep going. So ln of the absolute value of y, that's the integral of 1 of y, is equal to minus ln x plus some constant c. We take exponentials on both sides, and we rearrange here y is equal to 1 over x by a, where a is not equal to 0, right? Because a is e to the c over here, and there's no value c that you can plug in that'll give e to the c equal to 0. So y is equal to 1 over xa, or maybe a more recognizable way of writing it is that xy is equal to a. Yes?
What happens to the negative after you integrate it?
In front of the natural log of x.
Yeah.
Well, you take it inside the logarithm because you want to eventually get the exponential and the logarithm to cancel out. And when you take it inside the logarithm, you get x to the power of negative 1, which is the 1 over x there. Okay. And over here, we recognize this as being a bunch of hyperbola. So let's just go back up and think about what we have to do here. So I've drawn in, and I've actually drawn in too much, now that I think about this more carefully. Whoops. So what I've drawn in so far, the red hyperbole are the hyperbola that I've just found by doing this calculation. I've also drawn in the line y is equal to 0, which is this sort of separate solution. So I've drawn that line in. But we can see that there is actually one more. That over there is also orthogonal. So we've lost that somewhere. And it's not immediately clear where we've lost that. Hold on, let me actually just say these ones are being drawn in red. It's not clear where we've lost that. And I think where we have lost that is over here. Was it over here? At some point we... no, where did we lose it? Not over there. Did we ever divide by x? We must have divided by x or something. Oh wait, no, okay, right, sure. So this is, this differential equation is clearly not defined when x is equal to 0. So we should maybe just check x is equal to 0 separately as well. Turns out that in this case x is equal to 0 does work. Normally you wouldn't have to check x is equal to 0 because the differential equation you're trying to find this unknown function y. But this, because it came from a problem, this orthogonal curves problem, orthogonal trajectories problem, we should check it as well. All right, so I think that's everything. We'll come back next week and we'll start speaking about more interesting differential equations. Otherwise, enjoy your weekend.